Augies Worldwide. I'm Dave Casler, amateur radio call sign KE0OG, here with another episode of Ask Dave. This question comes from Don, Victor Echo 3, Oscar Victor Lima. He says he's trying to get back on the air after a 35-year layoff. This is a very common story. People have to put ham radio aside while the kids are doing this or they're getting their career going, but once they're empty nesters again, they like to get back into ham radio. I ran across one of your videos and like your understandable presentation. My question relates to verticals. I would like to better understand ground planes and earthing and the relationship between them. In a very short phrase, ground planes are counterpoises, they're capacitive. And earthing is actually a connection to earth and is resistive in nature. So they're different. However, they can be combined. So let's take a look and do a little bit about vertical antennas. Okay, a vertical is just what it implies, vertical. Let's look at a radio wave. A radio wave is doing this, okay? Sine wave. That's a horrible representation of a sine wave. But anyway, the radio waves can be polarized. Now, polarized means that if you're, and I'm looking end on into a radio wave, the voltage, and we're just measuring voltage here, this is kind of a representation, the voltage goes up and down this way. So if you were in the electromagnetic field and you were measuring it here, here, and here, you would see the voltage go up there, whereas if you were measuring out in these places, it wouldn't make much of an impact. That's a vertically polarized wave. A horizontally polarized wave goes this way. All right? Now, let me tell you something about the Earth. Here's the ionosphere. Ion. Okay. The signal comes up and hits this and is refracted, actually, back to Earth. Okay? This is a single hop, HF. Now, when I draw the ionosphere like that, I mean it. It's not smooth. It's kind of jagged. So you can get multipath like that, which causes fading. Anyway, let's look at this. Suppose this is a vertically polarized wave. Coming up here, it's going to hit this. What happens to it? It is reflected as two waves. Okay, there are two waves, the X wave and the O wave. And they are circularly polarized, and you get both of them coming out of here. They take slightly differing paths. Okay, one of these is right-hand circularly polarized, and the other is left-hand circularly polarized. Okay, they actually come down in two different places. So the wave that is coming down is circularly polarized, and it can be either way, right here. So the best antenna to pick this up would be a circularly polarized antenna pointed directly at where this is coming. Now, we don't know where that's coming from. We're down here. So what you actually get is elliptical polarization, to where this can be the vertical and this the horizontal, or vice versa, okay? Now, if you've got a wave like that, a vertical antenna right there would pick it up better than a horizontally polarized antenna, but they would both pick it up. Now, you've got most, and I can't remember, this is the ordinary wave, and this is the extraordinary pointed, the extraordinary and the ordinary. The ordinary has the most power. The X wave has less power, but comes down in a different place. Okay, this is not your standard textbook, technician book explanation of what goes on in the ionosphere. It is, however, explained very nicely in this book from the League called Here to There, Radio Wave Propagation, and this is written by Ward Silver with contributions from a whole bunch of other people. Ward Silver is an excellent writer, and this does not go into the calculus or anything, but it tells you very nicely about what is really going on in propagation. Nice book. I recommend it. prepare to have your mind blown. Okay, so now, if it's reflected off the ionosphere, then either a horizontal or a vertical antenna will pick it up. If, however, you are getting a ground wave, and you've got another antenna here that's vertical, you'll get most of the signal, but if you have a dipole, you won't. There's a lot of cross-polarization loss. Okay, but normally we work with the ionosphere, and we have that. So the fundamental antenna, unless we're dealing with wave antennas, which we're not, is the dipole. Okay, two sides, often fed at the center, sometimes off-center, sometimes at the end. They're all dipoles. Okay, there's a dipole. You can have a dipole vertically. Okay, now, if you put a mirror here, what you're going to see is the antenna on the top, and you look down into the mirror and you see an upside-down antenna. Okay? Think of the ground as a mirror. Okay, so you get waves coming off of here, you're going to get waves hitting the ground and coming off of here like that, just as though it were hitting the antenna that you see underground. So the ground has a tremendous effect on the way vertical antennas work. You've got antenna going this way, reflection here, or it could be a reflection here, or whatever. If you've got a wave this way, you've also got a wave this way. Okay, vertical antennas are very good in that direction. Now let's talk about real world. Okay, I showed a dipole cut in half, so that means a vertical antenna is 1/4 wavelength. That's the Greek letter lambda, which we use for wavelength. So if it's 20 meters is the wavelength, this is 1/4 of that, which is 5 meters, okay, which is about 15 or 16 feet tall. Okay? You can get whip antennas that long that you can put up like for a podocite or something like that. Now the question is, how do you create the mirror? Okay, for the reflection. Very little ground, unless it's soaked with salt water. And by soaked with salt water, I mean you're out in the wetlands by the beach, okay? Soaked in salt water. You don't need to do much down here except you've got the center of your coax coming here and the outside of your coax connected to something in the water. Normally, we have to create an artificial ground or something to reflect the waves off. This is where the radials come in. We put radials out here, okay, like that. Some manufacturers will have you believe that one radial is sufficient. That's baloney. I'd go with a minimum of 6 or 8. The length doesn't matter much, okay? I've built nice antennas with 10-foot radials. My Step IR, Big IR out back has like 30-foot radials, some of them. Others 25 feet, others are shorter. Okay, it's a potpourri. Here's what happens. This counterpoise, when the AC or the RF is going up, you are drawing in power held in capacitance out here. It's going up that way. When this turns around and goes down, you've got it coming back out over here. So we say that a counterpoise is something for the antenna to work against. For example, suppose you're trying to push a refrigerator in closer to the wall. And the whole surface here is covered in a puddle of oil. How do you do that? Well, you stand here and you push against it with your hands. And you're down here slipping and slipping and slipping. This thing isn't going to move. Okay, you need a nice, solid, dry surface so that you can come out here and push against that to push this into there. This is how this works. Okay? You've got something to work against, and that's what the radial field is. It acts capacitively. It stores energy in the form of the voltage, and as the thing moves the other way, it works in tandem with that. Now, that means that these tips right here are about the same voltage as the tip up here, which can be quite high. Be careful of them. put them where children, animals, whatever, won't come into contact with them. I use insulated radials, insulated wire. I just use the ordinary THHN house wire to put those things out there. You can buy this in spool form down at Home Depot, single conductor, which is actually stranded. It's got 7 strands. I love working with stranded wire because it is so much easier to work with than unstranded wire. I would recommend 14 gauge or higher. So 14, 16, 18, 20, 24, whatever. I put 14 gauge wire, sometimes 12 gauge wire down, always stranded, because that way it's stronger. If you step on it, it doesn't break it. Okay, if a deer trips over it, it doesn't break it. Now, after a while, you lay these on top of the ground, or if you've got like grass there, you can get a pizza cutter, okay, roll that along the surface to create a little slit, and behind you, you're pushing the wire down to the surface or a little bit below the surface. Okay, if you go below about 2 inches, these start acting as ground rods rather than radials, and you want them to act as radials. I lay mine on the surface. Now, if you go out there and look for the radials, they're hard to find because the grass and stuff has grown up around them, and that's fine. Now, what about, you asked about the ground, okay? Your cable comes out here. The center conductor connects to here. This is the half wavelength long. And then the outer conductor connects to the counterpoise. Now the outer conductor, back over here, you've got it connected to your lightning rod anyway. You can also, if you want to make sure that that stays balanced, you can drive a ground rod and connect it to that. And that's how I do it on my step IR, big IR. I've got an 8-foot ground rod out there, very thoroughly and carefully connected into the circuit. You can connect that, and that can help reduce common mode currents coming back or anything like that, because this and this act a bit like they're balanced. So you want to keep that ground rod in there. I'm talking about permanent installation. Clearly, if you're setting this up for POTA, you're not going to drive a ground rod. Don't go on to park property and drive ground rods. You could go through a sprinkler line, you could go through a water line, you could go through a sewer line, you could go through electric lines that were buried underground. Don't put not even a tent stake into the ground. Okay? So this is how verticals work. And I've talked to you about radials on the surface. You can hold them out if you want with a little spike or something if you're in your own backyard. Whatever you don't, they don't have to be straight. Because what happens is this acts like a big mesh, and you see the wave going out and then the wave coming back in from the ensemble of the radials. Okay? Now, this is if you've got a ground-mounted vertical. You can do other things. If you have, say, up on your roof, a vertical, you can put 2 counterpoises in for each band, but these have to be tuned. So these have to be 1/4 wavelength, 1/4 wavelength, and you need a pair for each band. And then here's your vertical. And I assume it's got traps and stuff on it for different bands and so on. You can put traps in these if you want to, but better to put them all out there. Traps, what traps do is they are a compromise in that they reduce the bandwidth of the antenna. So it might only work on half the band. So you have to tune it for the half band you want. This is a problem for people who like both single sideband and FT8. They're at opposite ends of the band. You need the whole band. Now, another thing that you can do. Let's take a wire and we'll put some loading on it, some traps, a little loading down here and so on. And we'll put a 49-to-1 balun, something like that, right at the bottom. Okay, and this thing up here is a half electrical wavelength, shortened because of all the traps and everything. Shortened, this can be little as 18 feet high, but you put these up. Now, it has a counterpoise built in. It has these big, 4 of these big things out here, okay? That's your counterpoise. And then you mount this about 10 feet above the ground. And make sure you guy that point there, and you might end up having to guy it in the middle, okay? Now, use rope, guys. UV resistant company that makes great rope for guys is Mastrant. And I actually use their 1/8 inch, which has several hundred pounds force before it breaks. And I have yet to have an antenna break one of these and fall over, even in our roughest winds. Okay, now, I don't live in Florida. We don't have hurricanes here. The highest wind I've ever seen here is 57 miles an hour. And the antenna stood up just fine. So anyway, these right here are the so-called radialless antennas. They're a half-wave length long. They're end-fed against a counterpoise. Here, this mast can be grounded, and the outside of the coax will also attach to the mast, the way these things are set up. Okay, so that tells you a little bit about verticals. You got lots of opportunities to make them work. Verticals can be made out of just about anything that's nicely conductive. Piece of copper wire, aluminum tubing, things like that. There is an antenna that comes out of England that's actually a fan vertical. And it works very, very well. I got one, I put it up, and the thing works very well. So you can do things like that for multiband types of things, just like you would do for a dipole, fan dipole, except you're just fanning half of it, and then the rest works against the radials. It's a very interesting antenna. So there you have it. I hope that helped a little bit with kind of an explanation about vertical antennas. So if you want to share this with people who would just like to learn about antennas, there you go. Until we next meet, 73.